handing an engineering team a coding agent, forgetting to set a hard usage limit, and receiving a bill for $500 million. That is a real incident from 2026. One major tech company blew through its entire annual AI coding budget by April. In another instance, a developer let an autonomous 4-agent LangChain loop run unmonitored for 11 days, and it burned $47,000. Enterprise data shows per-developer token consumption rising more than 18 times over a 9-month period. Operating an agent is like leaving a taxi with the meter running in the corner of a room. Every thought the agent has, every file it reads, and every internal check it makes clicks that meter up. A traditional chatbot takes one short ride. One question, one answer. Because individual tokens cost fractions of a cent, that single ride is cheap. An agent, however, runs a continuous loop. It reasons, acts, and loops back to think again. That continuous thought is expensive. The financial drain became so severe that the Linux Foundation established a dedicated cross-industry body solely to track and curb runaway token costs. By 2026, the bottleneck shifted from technical capability to raw affordability. The success of an agent now depends on an organization's ability to sustain the high-velocity computation required to keep the meter running. This diagram shows the mechanics of an agentic loop. At every cycle, the model moves through 3 central nodes. It perceives input, it reasons and plans, and it calls a tool to act. Each of those steps requires an API call. Following this green return arrow reveals a severe structural flaw. At every single iteration, the agent must resend the entire accumulated history of the conversation back to the model. Look at the token meter box here. Step 1 is a small prompt. By step 90, the system is resending 89 prior steps just to take one more action. The cost curve is quadratic, compounding with every cycle. Tool calls accelerate this compounding math. When the agent fetches a web page or queries a database, those massive blocks of text land in the context window and get resent on every subsequent step. Add a swarm of subagents to the process, and the effect multiplies. Each autonomous agent builds and resends its own heavy context window. Gartner's analysis quantified this math, calculating that agentic tasks require 5 to 30 times more tokens than standard generative chatbot churns. Runaway costs are a structural property of the loop itself. You cannot fix the bill by simply asking the model to be cheap. You have to actively engineer the architecture against the compounding math. The first line of defense is strict. Never pay to process the exact same input or thought twice. This begins with explicit prompt caching. By defining static system prompts and tool specifications, you can instruct the provider to cache that prefix. Reading from that cache applies a massive 90% discount compared to processing new tokens. Several major model providers now execute this exact prefix caching automatically, requiring zero configuration from the developer. This diagram illustrates semantic caching. Instead of matching identical text, the system takes an incoming query and embeds it by its underlying meaning. If someone asks for a refund window, and later someone else asks how long they have to return an item, the semantic cache recognizes it as the same question. Following the green pathway, a semantic cache hit serves the stored response instantly. It requires 0 model tokens, dropping the cost of that API call entirely. If the query represents a new meaning, the yellow pathway shows a cache miss. The system routes the query to the model, pays the full token cost, and stores the new answer for the future. But semantic caching carries a strict risk. If an answer depends on real-time data, account state, or specific permissions, serving a cached response means serving a stale truth. Sternly, a well-placed cache hit saves real capital. A reckless cache hit serves incorrect or exposed user data. Strict invalidation logic is a critical requirement. By the late stages of an operational loop, the vast majority of the context payload is useless noise. Resolved errors and outdated tool responses sit in the history, draining the budget. Context pruning forces the agent to maintain a tight running summary of its actions, instead of carrying a bloated, verbatim transcript. Advanced architectures use prompt compression. A specialized, smaller model evaluates the text and scores the actual information value of every single token. That small language model actively strips out low-value filler words and redundant phrasing before the expensive frontier model ever sees the prompt. Budget controllers manage this process by compressing different parts of a prompt unevenly. They preserve strict operational instructions while heavily compressing verbose code examples. In typical production environments, this yields 4 to 10 times compression ratios, with almost no measurable loss in accuracy. Paying a premium reasoning model to read filler text is a waste of capital. Using a cheap model to strip the filler first slows the entire meter down. The routing philosophy is straightforward. Do not send a complex frontier model to do basic data extraction or list formatting. There is a massive 15 to 20 times price gap between an economy tier model and a premium reasoning tier. This visual shows the architectural concept of a routing cascade. An incoming task enters this central purple router node, which evaluates the complexity of the query up front. The vast majority of simple, everyday tasks follow the green pathway, defaulting directly to the cheap economy tier model. The yellow pathway dictates the escalation cascade. Only genuinely difficult cases, or responses where the economy model returns a low confidence score, trigger the expensive tier. Open-source benchmarks demonstrate that trained routers can maintain 95% of peak quality while only sending 14% of the traffic to the strong model. Modern frontier architectures and gateway proxies now build this exact routing and fallback logic natively into the infrastructure. For engineers, the escalation rate becomes the most critical live variable to monitor in a cascade system. If too many queries escalate, the cost savings vanish. Spending a tiny fraction of a cent upfront to route a query properly prevents spending massively on back-end reasoning power. In most current architectures, cost is entirely invisible to the agent itself. The financial reality only surfaces on an engineering dashboard long after the run is complete. The required architectural pivot gives the agent an explicit Tulpin budget it can actively monitor while making its plans. Watch how this logic tree operates. A central planner node evaluates 2 branching actions, actively weighing the cost metric of spinning up multiple verifiers directly against its remaining budget. This creates a system where the agent calculates utility versus cost. It can determine that a good enough answer is the correct choice because a perfect answer exceeds the allowance. Some engineers dismiss this as premature optimization, but cost stops being premature the exact moment an architecture scales to multi-step or multi-agent loops. To enforce this, gateways require hard guardrails and rate limits as a final backstop against a single loop spiraling into a massive bill. Caching, pruning, and routing combine to cut API spend by up to 90% while strictly preserving output quality. Efficiency is a primary cognitive function. In a cost-aware architecture, the agent treats its budget as a fundamental variable in every cycle of reasoning. For neurals.ca, I'm Imran.